Hello, my name is Kevin Alvarado, and this is the artificial blood vessels presentation. So the artery that we chose to look at was the left pulmonary artery, otherwise known as the LPA. The LPA is a major artery in the human body, as its main function is to move deoxygenated blood away from the heart and towards the respective lung. Properties and dimensions for the right and left pulmonary artery are usually going to be equivalent, meaning that the pressure and flow rates that we've determined can be used for either the left or right pulmonary artery. Also, the materials that we selected for the simulation can be considered in other designs of different artificial blood vessels as well, as each of the three materials that we've chosen are going to be biocompatible with the human body. It was determined that the average blood flow rate in the LPA is going to be 186 milliliters per second. Knowing the density of blood, we can figure out the mass flow rate, which was 0.185 kilograms per second. It was also determined that in the LPA, the normal systolic pressure is going to be right around 2,000 pascals. For an average male, the pulmonary artery has a diameter of 1.2 inches or 30.5 millimeters and a wall thickness of 1 millimeter. So the first material we chose to look at was polyethylene. You can see it has a price of 96 cents per kilogram. It's widely used for medical applications as it has a zero water absorption and low coefficient of friction. This polyethylene material is fairly economical and has good mechanical properties with a yield strength of 28 megapascals, density of 960 kilograms per meter cubed, and a Young's modulus of 600 megapascals. The second material we chose to look at was silicone. You can see it also has a price of 44 cents per kilogram. Overall, this material is very durable and will be able to perform over a long period of time, as it has a good retention of flexibility with fairly strong mechanical properties as well. The yield strength of 120 megapascals, density of 2,330 kilograms per meter cubed, and a fairly large Young's modulus of 112,400 megapascals. The final material we chose to look at was polycaprolactone, otherwise known as PCL. As you can see, the PCL has a fairly high price, sitting right around $4.19 per kilogram. PCL is a biodegradable thermoplastic polyester, as well as it having a history of being widely used for artificial blood vessels. It could also be used for 3D printed applications with a density of 1,020 kilograms per meter cubed and Young's modulus of 35.5 megapascals. So as you can see, this is how we set up the simulations. Each material is going to have a model with lengths of 1 millimeter, 10 millimeter, and 100 millimeter longs. We previously determined that the mass flow rate of blood in the LPA is going to be 0.185 kilograms per second, while the outlet pressure is going to be right around 2,000 pascals. Using these pressure results that we get from the SolidWorks simulation, we're able to find hoop stress as well as the hoop strain, and this hoop strain will be used to calculate your percent in expansion within the blood vessel. E right here is going to be the Young's modulus. This symbol right here is the hoop stress that we will determine from this formula. We know that the diameter is 30.5 millimeters and a wall thickness is 1 millimeter. Here you can see the results that we obtained from the simulation for the polyethylene material. At 1 millimeter, the internal pressure was determined to be 2,012.6 pascals. For 10 millimeter long pulmonary artery, internal pressure was determined to be 2,000.8 pascals. And for the 100 millimeter length artery, it was determined to be 2,668.2 pascals. As you can see, we calculated the hoop stress. For the 1 millimeter and 10 millimeter long vessels, the hoop stress was right around the same at about 30,000 pascals, while the 100 millimeter length vessel experienced the largest hoop stress at 40,690 pascals. Hoop strain expansion for this material was relatively small, at a factor of 10 to the negative 4th% expansion rate. The silicone pressure results are right here. As you can see, for a 1 millimeter long vessel made out of silicone, the internal pressures stay the same at 1,999.4 pascals. For the 10 millimeter long and 100 millimeter length vessels, the internal pressure was also fairly close at 2000.1 and 2002.4 pascals respectively. You can see that the hoop stress in pascals is going to be relatively similar for each length of the silicone vessel, as well as the hoop strain expansion all being the same at 2.6%. Looking at the polycaprolactone results, we can see that for the 1 millimeter long vessel, the pressure stayed at 1,999.4 pascals, while the 10 millimeter long vessel experienced an internal pressure of 2,000.16 pascals. The 100 millimeter length vessel experienced the largest internal pressure of 2,040.15 pascals. Using those pressure values, we were able to determine the hoop stress. Once again, the 100 millimeter length vessel experienced the largest internal hoop stress with 31,127.5 pascals. This large hoop stress is going to give us the largest hoop strain expansion for this material at right around 8.4 times 10 to the negative 3%. You can see that all of the hoop strain expansion percent values are going to be relatively small, meaning that the blood pressure in the LPA is not going to cause the vessel to expand too much. So we're looking at a worst case scenario. We analyzed the 10 millimeter long blood vessel for all three materials, polyethylene, silicone, and polycaprolactane. To look at this worst case scenario, we multiplied the original blood flow rate by 5 times. We get a new flow rate of 0.925 kilograms per second. And in the SolidWorks Simulation Manager, we created total or maximum pressure goals for each of the vessels to determine the highest pressure that these vessels will experience with this worst case scenario blood flow rate. As you can see, polyethylene had a new internal pressure of 2,099.36 pascals. Silicone experienced an internal pressure of 2,036.4 pascals, while the PCl experienced an internal pressure of 2,036.4 pascals. Looking at these results compared to the normal case results, the internal pressure rates are going to be fairly similar. So knowing this, we can make a conclusion with the expansion rate being fairly small for each of these worst case scenarios as well. Alright, so due to all materials experiencing small strain expansion percentages, it can be concluded that each material will be a suitable candidate as an artificial LPA. The PCl had the highest price of all the materials, but as I said, it has been used for artificial blood vessel prosthesis. So this is always a good choice, as we know that it's going to work for a long period of time. It's going to have a high durability as well. The next best material that was chosen was the silicone. Its high flexibility and material properties suit the application very well, and it is also a much cheaper option than the PCl with the price of 44 kilograms per second. And that is all I have for you. Thank you very much.